right now, sitting in titanium tubes on the floor of a Martian crater. There are rock samples that may contain the first evidence of life beyond Earth, and no one has read them yet. Subscribe, there's a new one every few days. This is White Space Settle In. There is a planet in our solar system that has refused to let us forget it. For centuries, it burned in the night sky, rust-colored and steady, too bright to ignore, too far to reach. We gave it a name drawn from war. We filled it with imagined civilizations, and when we finally sent machines to look at it up close, what we found was stranger, older, and more complicated than any of the stories we had told ourselves. This is the story of Mars. Not the Mars of science fiction, not the Mars of simple answers, the real one. A world that once held water and warmth and maybe, just maybe, something we have not yet been able to name. A world we are now circling, rolling across, drilling into, photographing from centimeters away. A world that some people seriously intend to make a home. To understand why Mars matters, you first have to understand what it actually is. Mars is the fourth planet from the Sun, roughly half the diameter of Earth. Its surface area, though smaller than Earth's total land mass, contains some of the most dramatic geology in the solar system. The Tharsis volcanic plateau rises several kilometers above the surrounding terrain and hosts 4 massive shield volcanoes. The Valles Marineris, a canyon system stretching nearly 4,000 kilometers from end to end and plunging up to 7 kilometers deep, makes the Grand Canyon look like a drainage ditch. Ancient impact craters pock the southern highlands, some of them billions of years old, their rims worn down by wind and time, but still clearly visible from orbit. And across the equatorial region, there are the remnants of what planetary scientists believe was a world dramatically different from the one we see today. A Martian day called a sol lasts 24 hours and 37 minutes, close enough to Earth's day that early colonists would adapt without great difficulty. Mars has seasons driven by an axial tilt of about 25 degrees, similar to Earth's 23.5 degrees. It has polar ice caps, one composed largely of water ice and one of frozen carbon dioxide. It has weather, dust storms, clouds, fog in the valleys in the early morning hours. The average temperature on Mars is around minus 40 degrees Celsius. On a warm summer afternoon near the equator, the surface temperature can briefly rise above zero. By the time the sun sets, it drops to minus 90 or below. The atmosphere is thin, less than 1% the pressure of Earth's atmosphere at sea level, composed almost entirely of carbon dioxide with trace amounts of nitrogen, argon, and oxygen. You could not breathe it, you could not survive it unprotected. A person standing on the Martian surface without a suit would lose consciousness in less than a minute. And yet we keep sending things there and they keep sending data back. From orbit, Mars looks deceptively simple. A red-brown disk dusted with white polar caps. But the images returned by orbiters and surface rovers reveal a world of layered complexity. There are volcanic plains as flat and barren as any desert on Earth. There are highlands cratered so densely they resemble the surface of the moon. There are valleys carved by ancient water and ancient ice, and river deltas preserved in the rock with a clarity that makes them look as if they were formed last season rather than 3 billion years ago. Among the strangest things visible in the Martian sky are clouds. On a planet with almost no atmosphere, clouds should barely exist. But they do, thin, wispy formations drifting through the upper reaches of the atmosphere, appearing and vanishing with the seasons, occasionally forming in great arching streaks above the summits of the Tharsis volcanoes. For a long time, climate scientists struggled to explain how they formed at all. At the altitudes where these clouds appear, there is almost no water vapor and nothing obvious for ice crystals to condense around. The answer came from a source no one had initially considered: the continuous rain of meteoric material entering the Martian atmosphere every day. When small meteoroids burn up in the upper atmosphere, they leave behind microscopic particles of metallic and silicate dust, what researchers now call meteoric smoke. These particles, too small to see individually, drift through the thin air and act as condensation nuclei. Water vapor, scarce as it is, freezes onto them, forming tiny ice crystals that aggregate into clouds. The same mechanism produces the noctilucent clouds seen in Earth's mesosphere, those electric blue veils that appear just after sunset at high latitudes, though the physics on Mars plays out at much higher altitudes and in far thinner air. What made this discovery particularly interesting was not just the clouds themselves, but what they do to the rest of the Martian weather system. When researchers incorporated meteoric smoke into climate models of Mars, the entire behavior of the atmosphere shifted in ways that were not predicted. The presence or absence of these high-altitude clouds can shift regional temperatures by 10 degrees Celsius or more. They affect the height and behavior of the atmospheric boundary layer near the poles. They alter the transport of water vapor across latitudes. They interact with dust cycles in ways that scientists are still untangling. Mars, it turns out, has a climate. Not a simple one, a complicated, coupled system in which chemistry, physics, and dynamics interact across enormous ranges of altitude and season. And the key to understanding it was a kind of invisible smoke made of vaporized meteorites. Water left its signature on Mars long before any spacecraft arrived to look. Early astronomers noticed features on the Martian surface that resembled drainage networks, branching channels flowing toward ancient basins. When the Viking orbiters returned their first high-resolution images in the 1970s, those channels became undeniable. Mars had been carved by something fluid, moving fast over long periods of time. The subsequent decades of orbital observation have only deepened the mystery. Analysis of hundreds of ancient riverbeds, their width, their depth, the meanders they followed, the sediment fans they left at their mouths, indicates that some of these channels once carried enormous volumes of water, not thin trickles, real rivers sustained over seasons or years, fed by precipitation or snowmelt or both. The hydrology implied by these features is not the hydrology of a briefly warm planet that got wet during an asteroid impact and dried out again in 1,000 years. It points to something more persistent, a climate capable of generating a genuine water cycle, with evaporation and precipitation, with seasonal flooding and seasonal drought, with the kind of sustained liquid water that on Earth has been the prerequisite for life. In the northern lowlands of Mars, a vast plain called Vastitas Borealis lies several kilometers below the surrounding highlands. It is unusually smoother than the ancient southern cratered terrain, smooth in the way that sedimentary seafloors are smooth, filled in by particles settling through water over millions of years. Its margins show features that look like ancient coastlines, including what may be wave-cut terraces and ancient beach deposits. Some planetary scientists have proposed that this plain was once the floor of a shallow ocean, not particularly deep, perhaps a few hundred meters at most, but enormous in extent, an area roughly comparable to Earth's Arctic Ocean, holding perhaps as much water as is currently locked in the Antarctic ice sheet. The debate about how wet and warm early Mars actually was has not been resolved. Some researchers argue that the evidence requires a warm, dense early atmosphere, supported by greenhouse gases like carbon dioxide, methane, and hydrogen, capable of sustaining liquid water across broad regions for extended geological periods. Others contend that the ancient climate was cold most of the time, with liquid water appearing only episodically during volcanic eruptions that injected greenhouse gases into the atmosphere or after large impacts that temporarily melted surface ice. The channels could have been carved not over millions of years of steady flow, but during geologically brief wet periods separated by long, cold, dry intervals. Both interpretations fit parts of the evidence. Neither fits all of it. But what is not in dispute is that the water existed, the minerals in Martian rocks recorded, clays and sulfates and carbonates that form only in the presence of liquid water are widespread across the ancient Martian surface. Wherever rovers have drilled, the rock chemistry tells the same story. Water was here. The question of what lived in that water, if anything did, is one of the central questions driving every mission we send. On the slopes of Martian mountains and across ancient impact basin floors, there is evidence of ice that moves. Martian glaciers, smaller and slower than their terrestrial counterparts, have shaped the landscape in ways unmistakable to anyone who has studied glacial geology on Earth. The rounded ridges, the parallel scratches in rock surfaces, the horseshoe-shaped hollows, the elongated debris mounds pushed to the margins of ancient ice masses. All of these features appear on Mars in the same spatial relationships that they occupy in the glaciated highlands of Antarctica or the fjord coasts of Norway. These glaciers are not mere relics. Data from orbiting spacecraft show that some of the ice deposits on Mars are still deforming slowly under their own weight, still responding to seasonal changes in temperature and pressure. The planet is not frozen in geological time, it is frozen in ice, and the ice is moving. Among the more visually striking features on the Martian surface are structures that, when first imaged from orbit, looked unlike anything anyone had seen before. Dark branching forms spread across the bright surfaces of southern polar sand dunes, thousands of them, some reaching hundreds of meters in length. Their shapes reminiscent of spiders or river deltas or cracks in drying mud. They appear in spring, grow through the warm season, and fade by the following winter. They are dynamic, they seem almost alive. They are not alive, but the process that creates them is among the most dramatic geological phenomena documented on another planet. During the Martian winter, carbon dioxide freezes from the atmosphere onto the surface of the southern polar dunes, forming a layer of dry ice up to a meter thick. Beneath this layer, sunlight continues to penetrate through the semi-transparent ice, warming the dark sand beneath. As spring arrives and surface temperatures rise, the CO2 ice at the base of the layer reaches its sublimation temperature and begins converting directly from solid to gas. Pressure builds in the sealed space between the expanding gas pocket and the overlying ice sheet, the pressure of an invisible bubble growing beneath the frozen surface. Eventually, the ice ruptures. Gas erupts through the crack at high velocity, carrying with it dark sand and dust from the dune surface below. This material rises in a plume, catches the Martian wind, and falls back in dark fan-shaped deposits that are visible from orbit. Each eruption carves its channel a little wider. Season after season, the same vents reactivate, deepening the channels that radiate outward from each rupture point. From above, the result looks like a spider, a central hub with branching channels spreading in every direction. The Martian landscape is not passive. Even now, on a cold and quiet world, forces are reshaping its surface every spring. 4 billion years ago, the Mars we see today did not exist. The ancient planet was warmer and wetter, wrapped in an atmosphere thick enough to support liquid water across wide regions of its surface. Volcanic activity was intense, driving substantial greenhouse forcing. The core was still generating a global magnetic field. Impact cratering continued at a high rate, each major strike releasing enough energy to melt surface ice across thousands of square kilometers and temporarily heat the atmosphere. Whether that early Mars harbored life remains the central unanswered question in planetary science. The conditions necessary for life as we understand them: liquid water, Organic molecules, energy sources, mineral surfaces for chemistry to work on were all present. If life arose on Earth within a few 100 million years of the planet's formation, as the geochemical record suggests, then the emergence of life on early Mars was at least plausible. Whether it happened and what became of it if it did, we do not yet know. Standing on the Martian plains and looking toward the northwest, on a clear day you would see something that would take time to understand. At first it might not register as a mountain at all. It is too large. The mind refuses to scale it. It feels not a portion of the horizon, but the horizon itself, a vast, gently rising incline, its slopes disappearing over the curvature of the planet long before they reach the summit. This is Olympus Mons, the largest volcano in the solar system, the largest mountain by any reasonable measure of any planet we know. Olympus Mons rises approximately 22 kilometers above the mean surface elevation of Mars. Its base stretches more than 600 kilometers across. At its summit, a caldera complex, 6 nested craters deep, plunges nearly 3 kilometers into the rock. The volcano is so large that, standing anywhere on its slopes, you could not see the caldera rim. It lies beyond the horizon, hidden by the curvature of Mars itself. And standing at the caldera rim, you could not see the escarpment at the base. That too lies beyond the curve of the world. Olympus Mons is too big to see. It can only be understood from space. To appreciate what climbing it would mean, consider the most demanding mountain ascent in human experience. Mount Everest, 8,849 meters above sea level, has been summited more than 10,000 times since Edmund Hillary and Tenzing Norgay first reached its peak in 1953. The death toll stands above 300. Climbers face avalanche, frostbite, hypoxia, cerebral and pulmonary edema, and the slow cognitive degradation that comes from spending weeks at altitudes where each breath delivers less than a third of the oxygen available at sea level. A standard expedition takes 2 months with multiple acclimatization cycles, camps established at progressively higher elevations, and carefully managed ascent rates designed to give the human body time to adjust to conditions it was not designed for. Olympus Mons is more than twice the height, but the comparison to Everest is misleading in ways that matter. Olympus Mons is a shield volcano built over millions of years by the slow accumulation of thin, fluid lava flows spreading in all directions from a central vent. Its average slope is between 2 and 5 degrees. The gradient is less steep than many bicycle paths. You could, in principle, drive a wheeled vehicle to the summit without the terrain itself presenting any serious mechanical obstacle. The obstacle is the environment. The atmospheric pressure at the summit of Olympus Mons is approximately 2% of the already negligible Martian surface pressure. At the Martian surface, pressure is already less than 1% of sea level pressure on Earth. At the summit of Olympus Mons, the air is barely distinguishable from vacuum. Anyone attempting the ascent would require a fully pressurized suit, not supplemental oxygen but complete life support, capable of maintaining internal pressure, temperature and atmospheric composition through weeks of continuous operation. Any failure, any breach would be fatal within seconds. The temperature swings are violent. Martian summer days near the equator can warm the surface to near freezing. Martian nights can drop to minus 90 Celsius. At the summit, the temperature range is even more extreme, and the thermal cycling from the warmth of the afternoon sun to the brutal cold of night would stress every mechanical component in a suit or vehicle. Lubricants that function on Earth become rigid. Seals that hold at room temperature contract and fail. Materials that survive moderate temperature swings crack and fracture when subjected to daily oscillations of 100 degrees Celsius or more. The radiation environment is severe. Mars has no global magnetic field. Its thin atmosphere provides almost no shielding against the cosmic rays and solar energetic particles that constantly bombard the inner solar system. A person living and working on the Martian surface accumulates a radiation dose at a rate that, over a year, would be hundreds of times the safe annual limit for radiation workers on Earth. The summit of Olympus Mons, above most of the remaining atmospheric shielding, would be even worse. And then there is the caldera. The rim of the Olympus Mons caldera is bounded in places by cliffs rising 4 to 6 kilometers, vertical or near vertical drops into a void so large that you cannot see the far side. Crossing from the outer slopes to the interior of the caldera would require technical climbing. Rope work, protection placed in volcanic rock whose mechanical properties have never been tested by human hands, in a pressurized suit that limits tactile feedback and range of motion at temperatures where even the best mountaineering equipment would be operating at the edge of its design envelope. On Earth, in the most demanding alpine conditions imaginable, an Everest ascent takes 2 months. An ascent of Olympus Mons, accounting for the vast horizontal distance to be covered, the need to haul all life support, the absence of any possibility of rescue, and the technical challenge of the caldera rim would take several months at minimum. It would require a starting base with pre-positioned supplies, vehicles capable of operating continuously in the Martian environment, and technology that does not yet exist. But Olympus Mons is not infinitely high. Physics does not prohibit the summit. It simply requires more than we currently have. And that distinction between physically impossible and merely extraordinarily difficult is the margin in which human exploration has always operated. The history of our attempts to reach Mars is a story of failure, persistence, and hard-won success. The first spacecraft sent toward Mars were launched by the Soviet Union in October 1960, 2 probes that both failed to leave Earth orbit. Over the following decade, the Soviets and the Americans launched missions toward Mars with regularity and with roughly equal rates of catastrophic failure. Rockets exploded. Contact was lost days after launch. Spacecraft passed Mars without their cameras activating. Orbiters entered the Martian atmosphere and were never heard from again. The first successful Mars flyby was conducted by NASA's Mariner 4, which passed within 10,000 kilometers of Mars in July 1965 and returned 22 photographs. The images were grainy, low resolution, and showed a cratered moon-like surface. Mars, many scientists reluctantly concluded, was probably dead. Mariner 4 saw only a small fraction of the planet. It happened to pass over ancient cratered terrain in the southern hemisphere, missing the dramatic features that later missions would reveal. But the initial impression it created Mars as a cold, dead, heavily cratered world shaped scientific and popular thinking for the next decade. Mariner 9, arriving in 1970, reversed that impression completely. Entering Martian orbit during a planet-wide dust storm, the entire surface obscured beneath a churning orange haze. It waited for the storm to clear and then spent nearly a year mapping the planet in detail. What emerged from the dust was a world dramatically more complex and more interesting than the Mariner 4 images had suggested. Volcanoes the size of continents. A canyon system stretching a quarter of the way around the planet. River channels that unmistakably implied flowing water. A geologically active world with a complicated history. The Viking missions of 1976 were the most ambitious Mars program of the 20th century. 2 orbiters and 2 landers. The orbiters mapped the surface in unprecedented detail, producing photographic coverage from which scientists are still drawing insights today. The landers carried meteorological instruments, seismometers, cameras, and most provocatively, biology experiments designed to search directly for signs of life in the Martian soil. The biology results have never stopped being controversial. One experiment, called labeled release, injected radioactive nutrients into a Martian soil sample, and watched for the release of radioactive gas, which would indicate that something in the soil was metabolizing the nutrients. Gas was released abundantly. If the same result had occurred in a terrestrial soil sample, it would have been interpreted as strong evidence of microbial activity. But a companion experiment, one designed to detect organic molecules in the soil, found essentially nothing. Organic molecules are the chemical building blocks of all life as we know it. If living organisms were metabolizing nutrients in the soil, there should have been detectable organic chemistry. There was not. The consensus that emerged was that the labeled release result was produced not by biology, but by highly reactive inorganic chemistry, specifically oxidizing compounds in the Martian soil, perhaps hydrogen peroxide or perchlorate-driven reactions that mimicked biological metabolism without any organism being involved. Some researchers have challenged this interpretation ever since. The debate continues today, nearly 50 years after the experiments were conducted. But what the Viking results definitively showed was that the surface soil of Mars at the two locations sampled did not contain abundant viable microorganisms of the type that would have been easily detected by the instruments available. Viking 1 landed on July 20, 1976 and transmitted data for more than 6 years, long past its design lifetime, until a software command uploaded by ground controllers inadvertently disabled its antenna in 1982. Viking 2 operated for 4 years. Together they took tens of thousands of images, monitored Martian weather through multiple seasonal cycles, analyzed the soil chemistry, and demonstrated that landing on Mars and operating there for extended periods was achievable. After Viking, Mars exploration stalled. A succession of Soviet and Russian missions in the 1980s and 1990s cycles all failed before reaching their objectives. NASA's Mars Observer, launched in 1992, was lost 3 days before entering Martian orbit. One of the most demoralizing failures in the agency's history, coming after a decade of absence from the planet. It was not until Mars Global Surveyor, which reached Martian orbit in 1997, that a sustained program of scientific return from Mars resumed. The same year, Mars Pathfinder delivered a small rover named Sojourner to the Martian surface, the first wheeled vehicle ever to operate on another planet. Sojourner was modest. It weighed about 11 kilograms, moved at a maximum speed of roughly a centimeter per second, and traveled a total of about 100 meters during its 3 months of operation. But it demonstrated the fundamental principle. A rover could drive across the Martian surface, navigate obstacles, conduct measurements, and return data. Everything that came after was in some sense built on that proof of concept. Spirit and Opportunity landed on opposite sides of Mars in January 2004. Both were designed for a 90-day mission. Spirit operated for more than 6 years before becoming stuck in soft soil and eventually losing contact. Opportunity drove for 15 years and covered more than 45 kilometers before a global dust storm in 2018 coated its solar panels beyond the point of recovery. During those years, Opportunity found in the rocks of Meridiani Planum a chemical and mineralogical record of sustained liquid water, hematite spheres, small, round concretions nicknamed blueberries by the team, scattered across the surface in concentrations that form on Earth, only in water-saturated sedimentary environments. Layered sedimentary rock formed in standing water. Sulfate minerals that precipitate from evaporating briny water. Mars was not just wet. Mars had places where water stood for long periods. The Mars Reconnaissance Orbiter, arriving in 2006, has become one of the most productive scientific instruments ever sent to another planet. Its HIRIS camera high-resolution imaging science experiment can resolve features on the Martian surface as small as 25 centimeters across from an altitude of 300 kilometers. It has imaged active avalanches, fresh impact craters that appeared between successive passes of the orbiter, changing sand dunes and the tracks of every rover that has operated on the Martian surface. It images the Martian surface continuously, building a record of change over time that no single snapshot mission could provide. India's Mars orbiter mission, known as Mangalyaan, reached Martian orbit in September 2014, making the Indian Space Research Organization the fourth space agency to successfully operate a spacecraft in Mars orbit and the first to succeed on the first attempt. Mangalyaan carried instruments including a methane sensor, an imaging spectrometer, and a color camera. Its cost, approximately $74 million USD, was less than many Hollywood films about Mars, and it demonstrated that the capacity to conduct interplanetary science was expanding beyond the traditional space powers. The mission operated for nearly 8 years before contact was lost in 2022. Curiosity arrived in Gale crater in August 2012, lowered to the surface by a sky crane, a hovering rocket-powered descent stage that held the rover on cables and deposited it gently on the surface before flying away to crash at a safe distance. The landing system was audacious enough that mission controllers called it 7 minutes of terror, the time between atmospheric entry and landing, during which the spacecraft was on its own too far from Earth for any command to reach it in time to matter. It worked. Curiosity is a laboratory on wheels. Its drill can extract powdered rock from 2 centimeters below the surface. Its sample analysis at Mars instrument can heat rock samples and analyze the released gases with a mass spectrometer sensitive enough to detect organic molecules at concentrations of parts per billion. It has found thiophene, benzene, toluene, and other complex organic compounds in the ancient mudstones of Gale crater. It has measured seasonal and diurnal variations in the methane content of the Martian atmosphere, variations that imply an active source of methane somewhere, either geological or biological. It has documented a radiation environment that would accumulate over a 3-year Mars surface mission, a total dose large enough to raise a human crew member's lifetime cancer risk by several % in sight, which landed in Elysium Planitia in November 2018, approached Mars differently. Instead of moving across the surface, it stayed still and listened. Its SIS seismometer, seismic experiment for interior structure, was the most sensitive seismometer ever operated on another world. Over the following 4 years, it detected more than 1,300 Marsquakes, including events large enough to allow scientists to measure the velocities of seismic waves traveling through different layers of the Martian interior. The results revealed a crust roughly 20 to 37 kilometers thick, a mantle extending to about 1,560 kilometers depth, and a liquid iron core whose radius is between 1,790 and 1,870 kilometers, larger than many models had predicted. The planet retains internal heat. It still produces seismic events. Mars is not geologically dead. Perseverance landed in Jezero crater in February 2021. Jezero was chosen because it is the site of an ancient river delta, a place where, billions of years ago, a river deposited sediment into a lake that may have persisted for millions of years. If microbial life existed on early Mars, and if it left physical traces in rock the way that ancient microbial life on Earth left stromatolites and chemical biosignatures in Archean sediments, Jezero is one of the most promising places to find them. Among the remarkable things Perseverance has done is produce oxygen from the Martian atmosphere. An instrument called MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, uses electrochemistry to split carbon dioxide molecules into carbon monoxide and oxygen. In its test runs aboard Perseverance, MOXIE produced about 10 grams of oxygen per hour. This is not enough to support a human. Breathing requires about 500 grams per hour, but it is enough to prove the principle. The Martian atmosphere can be processed into breathable air. The planet's resources can be tapped. This is not a minor technical demonstration. It is the first experimental evidence that human survival on Mars does not necessarily require importing every breath from Earth. Above the Perseverance rover, a small helicopter named Ingenuity became the first aircraft to achieve powered flight on another planet. In April 2021, it lifted off the Martian surface, hovered for 30 seconds, and landed. The atmosphere of Mars is thin enough that generating lift requires rotor blades spinning at nearly 2,500 revolutions per minute, 5 times faster than a typical terrestrial helicopter. The Martian gravity, at 38% of Earth's, helps, but it was not certain that the approach would work until it did. Ingenuity was designed for 5 flights. It made more than 70 before a rotor blade was damaged during landing in early 2024. For 3 years, it served as an aerial scout, photographing terrain ahead of the rover, identifying landing hazards, and demonstrating that a future fleet of Martian helicopters could serve as the eyes of a human exploration program covering ground no rover could reach. The most visible driver of the shift from robotic to human Mars exploration is a private company that was founded in 2002 with an explicit mission to make humanity multiplanetary. SpaceX, over its first 2 decades, built a track record that few could have predicted. It developed the Falcon 9 rocket, partially reusable, dramatically cheaper per kilogram to orbit than the expendable vehicles it competed against, and demonstrated that rocket boosters could land on their own, be refurbished, and fly again. It won NASA contracts for cargo and crew delivery to the International Space Station, becoming the primary means of American access to orbit. And it began development of Starship, a fully reusable 2-stage launch system designed from the beginning not for low Earth orbit but for deep space, with Mars as the ultimate destination. Starship is large. The complete stack, Super Heavy booster plus Starship upper stage, stands taller than the Saturn V that carried the Apollo astronauts to the Moon. It is designed to carry 100 metric tons of payload to low Earth orbit in fully reusable mode. The upper stage can be refueled in orbit, extending its reach across the solar system. The propellant, liquid methane and liquid oxygen, was chosen specifically because methane can be manufactured from Martian resources using the Sabatier reaction, which combines carbon dioxide with hydrogen to produce methane and water. A Starship that lands on Mars could in principle be refueled using materials extracted from the Martian atmosphere and subsurfaced, then launched back toward Earth. The round trip becomes possible without carrying return propellant from Earth. The propulsion system at the heart of Starship is the Raptor engine, a full-flow staged combustion engine that burns its propellants more completely and more efficiently than any large rocket engine previously built. Both the fuel-rich and oxygen-rich pre-burner gases are fully combusted before entering the main chamber, extracting maximum energy from each kilogram of propellant. The Raptor's specific impulse, the measure of propellant efficiency, is among the highest of any operational chemical rocket engine. This efficiency matters for Mars because every additional unit of specific impulse reduces the propellant that must be carried, which reduces the mass that must be launched, which reduces the cost of every mission. The development of Starship has not been smooth. Early test articles at the Boca Chica, Texas facility exploded during pressure tests and low-altitude hop tests. The first integrated flight test in April 2023 ended with the vehicle tumbling out of control after stage separation and being destroyed by the flight termination system. The second test, in November of that year, reached the staging point but lost both vehicles shortly after. Subsequent tests progressively advanced the envelope. Higher altitudes, successful staging, re-entry of the Starship upper stage, and eventually the first catch of a returning super heavy booster by the launch tower's mechanical arms. Something no rocket in history had previously done. Each test was a step. Each failure yielded data that would have taken years and billions of dollars to gather through ground testing alone. The pace of development was unlike anything in the history of launch vehicle engineering. The mass budget of a Mars mission is the underlying engineering reality against which every plan must eventually be measured. How much material does it take to move a human crew to Mars, sustain them on the surface, and return them safely to Earth? The question was asked seriously for the first time by Wernher von Braun in the late 1940s. Von Braun, the German rocket engineer who had built the V2 and then became the architect of the American Saturn V, worked out a detailed Mars mission plan published in 1952 as a technical treatise called Das Mars-Projekt. His proposal called for an expedition of 70 astronauts traveling in a fleet of 10 spacecraft assembled in Earth orbit. The total mass that would need to be placed in orbit to launch this expedition, approximately 37,000 metric tons. In the early 1950s, this was pure fantasy. The largest rockets in existence could lift a few tons to orbit, not tens of thousands. But von Braun's calculation established a benchmark. By 1962, as the space age was barely underway, Sergei Korolev, the chief designer of the Soviet space program, was developing his own Mars mission concepts. Korolev's proposal was more modest. A crew of 3, launched from Earth orbit on a complex assembled from multiple launches, with a total orbital mass of roughly 500 metric tons, about 165 tons per crew member. Still far beyond the capacity of any existing or planned launch system, but scaled down from von Braun's vision by a factor of nearly 70. In the decades since, mission architects have continuously refined these estimates. The most optimistic scenarios, which assume significant in situ resource utilization, making propellant, water and air on Mars, rather than bringing it from Earth, bring the required orbital mass down further. But even these optimistic scenarios require placing hundreds of metric tons in Earth orbit before a crew can depart. And the mass per crew member scales roughly with the duration of the surface stay, the number of crew members and the degree to which consumables must be imported rather than manufactured. The practical implication of the mass problem is that the first crewed Mars missions will almost certainly not be large. Not the 100-person colony ships that appear in the most optimistic projections, but small crews of perhaps 4 to 8 people, staying on the surface for 18 months to 2 years and then returning. The infrastructure for those missions, habitats, power systems, resource extraction equipment would need to be in place before the crew arrives, delivered by robotic precursor missions over the course of several years. Building that infrastructure requires solving problems in autonomous robotics, remote operations, and construction in the Martian environment that have not yet been solved. The propellant challenge alone is formidable. A crew departing Mars needs enough propellant to escape Martian gravity, cruise back to Earth over 6 to 9 months, and decelerate into Earth orbit or re-enter the atmosphere. The mass of propellant required is a multiple of the dry mass of the spacecraft. If that propellant must be launched from Earth, it dominates the mission mass budget. If it can be manufactured on Mars, from Martian water ice electrolyzed into hydrogen and oxygen, or from Martian carbon dioxide converted to methane through the Sabatier reaction, the required Earth-launched mass falls dramatically. The entire viability of a crewed return mission may depend on the success of Martian resource extraction. The practical challenges of a crewed Mars mission extend well beyond launch vehicles. The journey from Earth to Mars using chemical propulsion takes between 6 and 9 months depending on the phase of the planetary orbit. During that time, the crew is confined to a volume that must contain not just living quarters but water recycling, air regeneration, food storage, medical equipment, and everything necessary to handle any emergency that arises without the possibility of outside assistance. A radio signal from Earth to a Mars-bound spacecraft, when the planets are at maximum separation, takes 22 minutes one way. Any question asked of Earth takes 44 minutes to receive an answer. The crew is operationally alone. The radiation environment during the transit is the most serious medical concern. Earth's magnetic field deflects most cosmic rays and solar energetic particles. Once beyond that shield, a spacecraft provides minimal protection. The data from Curiosity's radiation assessment detector, which was measuring radiation during its cruise to Mars in 2011 and 2012, indicated that the crew would accumulate more than 300 millisieverts during a 6-month transit, roughly 60% of the total radiation limit proposed for Mars missions over an astronaut's career. And that is just the journey there and back before accounting for time on the surface. The radiation risk is real, and it is not eliminated by any technology currently available. The mass problem is equally unforgiving. Estimates of what it takes to send a small crew to Mars and sustain them on the surface for the time required for the planets to realign for a return trajectory, typically 14 to 20 months, consistently run to hundreds of metric tons of material in low Earth orbit before departure. Life support consumables, food, spare parts, habitat materials, scientific equipment, medical supplies, surface vehicles, it adds up rapidly. Reducing this mass through in-situ resource utilization, making water, oxygen, and propellant from Martian materials is not just cost-saving. It is likely a prerequisite for the mission being possible at all. The Phoenix lander, which touched down in the northern polar region of Mars in May 2008, offers a useful illustration of what even a modest Mars surface mission can discover. Phoenix was launched in August 2007 and selected a landing site within the Martian Arctic, where orbital data had indicated subsurface water ice close to the surface. Its robotic arm was designed to dig into the Martian soil and deliver samples to instruments on the lander deck. Within the first few weeks, the arm exposed a white material just a few centimeters below the surface layer. White material that, when exposed to Martian sunlight and air, began to visibly shrink. It was sublimating. It was water ice, exposed to the Martian atmosphere for the first time in perhaps millions of years, converting directly from solid to vapor in the thin, cold air. The instruments aboard Phoenix confirmed what the orbital data had suggested and then went further. The soil in the northern polar region contains calcium carbonate chalk, which forms in the presence of liquid water. It contains perchlorate salts, which are chemically reactive oxidizers that suppress the melting point of water, could serve as energy sources for some types of microorganisms, and are relevant to understanding why the Viking biology experiments produced the results they did decades earlier. And the meteorological instruments aboard Phoenix detected snow falling from clouds several kilometers above the surface, water ice crystals descending through the thin Martian air. The precipitation evaporated before reaching the ground, but it demonstrated something important. Mars has an active water cycle, attenuated, thin, operating at temperatures and pressures that make it barely recognizable compared to what happens on Earth, but real. Phoenix stopped transmitting in November 2008, when the arrival of the polar winter cut off its solar power. It had operated for 5 months and 25 days, vastly less time than any rover mission, but the data it returned fundamentally changed our understanding of the Martian polar environment and the distribution and availability of water ice across the planet. All of this exploration of Mars eventually forces a question larger than any particular mission or instrument. If life exists or once existed on Mars, what kind of life might it have been? And by extension, what forms might life take elsewhere in the universe, on the billions of planets that exist under conditions nothing like our own? The life we know about every organism that has ever lived on Earth shares a specific biochemical foundation. Carbon is the structural backbone of molecules, water is the universal solvent inside cells. A handful of other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, assembled into proteins, nucleic acids, lipids, and carbohydrates. This is not arbitrary. These elements were chosen by billions of years of evolution from the options available under Earth-specific conditions. The question astrobiology asks is, on a planet with different conditions, would evolution choose differently? Carbon is exceptional as a structural element. A carbon atom forms 4 simultaneous chemical bonds, allowing it to build molecular architectures of essentially unlimited complexity. Straight chains, branched chains, rings, fused ring systems, 3-dimensional cages. The diversity of carbon compounds is so vast that the branch of chemistry devoted to it, organic chemistry, contains more known compounds than all other chemistry combined. Carbon is also the 14th most abundant element in the crust of the Earth and among the 10 most abundant in the universe. Its properties and its abundance make it a logical foundation for chemistry at biological scales. Water is similarly exceptional as a solvent. It dissolves an enormous variety of compounds. It is liquid across a temperature range broad enough to encompass most of the biologically relevant environments on Earth. It participates actively in metabolic chemistry. It expands when it freezes, unlike most liquids, which contract, meaning that ice floats on liquid water rather than sinking to the bottom. A property that has kept Earth's oceans from freezing solid during multiple global glaciation events. These properties are not coincidental from the perspective of life. Life on Earth evolved in water, and water shaped biology as much as biology shaped life. But water is not ubiquitous at the temperatures and pressures that prevail across most of the solar system. On Venus, it boils into vapor almost instantly. On the outer moons of Jupiter and Saturn, it freezes solid and remains frozen for billions of years. The temperature range in which water is liquid, 0 to 100 Celsius at standard pressure, is a narrow band that across the full range of planetary environments in the universe is the exception rather than the rule. If life is common in the universe, it is likely common in environments where water is not available in liquid form. Something else must serve as the solvent. Something else must take the structural role of carbon, or carbon must be used in ways radically different from what terrestrial biology employs. The field of astrobiology, formally established in the late 1990s, though the questions it addresses are older, studies these possibilities. It is a young field working from a sample size of 1. Every conclusion it draws is an extrapolation from a single example, but the extrapolations are not baseless. They are grounded in chemistry, physics, and planetary science. Before considering alternatives, it is worth asking why life on Earth uses the chemistry it does. All living organisms on this planet, every bacterium, every plant, every animal, every fungus, every archaea living in a hydrothermal vent, are built primarily from 6 chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 account for the overwhelming bulk of all biological matter. Everything else that appears in living tissue, calcium in bones, iron in hemoglobin, zinc in enzymes, iodine in thyroid hormones, is present in trace amounts compared to this core 6. The intuitive explanation for why life chose these particular elements is that they are abundant. And to a first approximation, this seems plausible. Hydrogen is the most abundant element in the universe. Oxygen is the third most abundant. Carbon is the fourth. Nitrogen is the seventh. These four make up the bulk of most organic molecules. It would make sense for life to be built from what is available, but the explanation breaks down under scrutiny. The second most abundant element in the universe is helium, and helium is a noble gas, chemically inert, incapable of forming stable bonds with other elements. It cannot be incorporated into complex molecules under any conditions relevant to biology. The noble gases as a group, helium, neon, argon, krypton, xenon, are all biologically useless regardless of their cosmic abundance. Neon is the fifth most abundant element in the universe. It does not appear in any known biological molecule. Phosphorus, meanwhile, is not particularly abundant. It does not crack the top 15 most common elements in the universe. It is not especially easy to access on planetary surfaces, where it tends to be locked in mineral forms with low solubility. And yet, phosphorus is indispensable to terrestrial life. It forms the backbone of every DNA and RNA molecule, the phosphodiester bonds linking nucleotides into chains. It is central to ATP and ADP, the molecules that store and transfer energy within every living cell. Without phosphorus, the energy metabolism and information storage systems of terrestrial life would collapse entirely. Sulfur is similarly not among the most cosmically abundant elements, but it plays essential roles in the chemistry of proteins, forming the disulfide bonds that hold protein structures together and appearing at the active sites of many critical enzymes. Why sulfur and not silicon, which is far more abundant and chemically similar? The question does not have a fully satisfying answer. It may be that the specific chemistry of early Earth, the composition of its oceans and atmosphere, the minerals available at hydrothermal vents, the specific reactions that happened to run in the early prebiotic environment selected for sulfur over silicon in ways that were essentially contingent. Had the early Earth been different, the biochemical inventory might have been different. Or there may be deeper chemical reasons why sulfur is a better choice for biochemistry under Earth-like conditions, reasons that have not yet been fully articulated. What this tells us is that life does not simply use whatever is most abundant. Life uses whatever works. The selection of the 6 core elements is not a direct consequence of cosmic abundance, but a product of billions of years of chemistry operating under a specific set of physical and chemical constraints. Change those constraints, change the temperature, the pressure, the composition of the atmosphere, the available minerals, the presence or absence of particular solvents, and the selection might be different. This is the foundation on which astrobiology builds its speculations. It is not speculation in the loose sense of idle fantasy. It is disciplined extrapolation from known chemistry into environments that no terrestrial life could survive, asking not what life is based on our single example, but what life could be based on the full repertoire of chemistry that physics permits. And the answer from chemistry alone is that the possibilities are far wider than our single example suggests. The question of what life on another planet might look like, physically, behaviorally, at the level of visible form rather than molecular structure, is one that planetary scientists and astrobiologists approach carefully, because the temptation to import assumptions from Earth is almost impossible to resist. Every fictional alien ever imagined by human writers and filmmakers has, with rare exceptions, been humanoid, bilateral symmetry, limbs arranged in pairs, sensory organs clustered at one end, a centralized nervous system. Even the most deliberately alien depictions in science fiction tend to be variations on a body plan familiar from Earth: an insect scaled up, a cephalopod given intelligence, a reptile given culture. But the humanoid body plan is not universal even on Earth. It is a body plan of the vertebrates, one branch of one kingdom of life on one planet. Starfish have five-fold radial symmetry. Sea anemones have radial symmetry of a different kind. Sponges have no symmetry at all and no nervous system. Trees are modular organisms that grow by adding units, branches, leaves, rather than developing according to a fixed body plan the way animals do. Slime molds spend part of their life cycle as individual single-celled organisms and part as aggregate structures behaving collectively. Life on Earth is already far more varied, far stranger, far more inventive in its architecture than the humanoid template would suggest. On a planet with different gravity, different atmospheric composition, different temperature regimes, different available energy sources, the evolutionary pressures that shape body plans would be different. On a low-gravity world, large body size would be less energetically costly, and structures that would collapse under their own weight on Earth could be stable. On a high-gravity world, the opposite compact, dense, low-profile body plans in an environment without light, a subsurfaced ocean, a world perpetually shrouded in cloud. The sensory emphasis would shift from vision to other modalities: chemoreception, pressure sensing, magnetic field detection, electrical sensing. In an environment where the primary energy source is chemical rather than solar, the architecture of metabolism would be fundamentally different from photosynthesis. And if the biochemistry itself is different, if the structural element is silicon rather than carbon, if the solvent is ammonia rather than water, then the physical forms that emerge from that biochemistry might be unrecognizable, not just as life, but as organized matter of any kind. A silicon-based entity growing slowly at high temperature and high pressure in the deep interior of a rocky planet might manifest as a pattern in a crystal lattice, a structured arrangement of atoms that stores and processes information and reproduces by directing the growth of similar structures in adjacent material. It would not have a nervous system in the terrestrial sense, it would not move rapidly or consume prey or produce offspring in a recognizable way. Viewed on a human timescale, it would simply look like rock. The practical implication of this is uncomfortable. We might not recognize life if we found it. The instruments on the current Mars rovers are designed to detect biosignatures that would be produced by carbon-based life, similar in basic chemistry to Earth life. They look for organic molecules, for isotopic ratios associated with biological processes, for mineral structures produced by metabolic activity, for cell-like morphologies in rock. If Martian life, past or present, used a sufficiently different biochemistry, a rover might drive right through it without the instruments registering anything unusual. This is one of the strongest arguments for returning physical samples from Mars. A rock in a laboratory can be subjected to every technique known to chemistry and physics. The sample can be sliced thin and examined with electron microscopes capable of resolving individual atoms. Its isotopic composition can be measured with mass spectrometers sensitive to 1 part in a billion. Its organic content can be extracted, separated, and characterized with instruments that would fill a building and cost more than any rover ever sent to Mars. If a biosignature is there, however subtle, however chemically alien, laboratory analysis offers a chance of finding it that no in situ instrument aboard a rover can match. There is one more possibility that deserves consideration, one that brings the question of alien biochemistry uncomfortably close to home. Some researchers have proposed that life with radically different chemistry does not necessarily require a different planet. It might exist right here, on Earth, in environments we have barely begun to explore. The deep subsurface of Earth, below a kilometer of rock, at temperatures and pressures that would kill any surface organism, hosts an extraordinary ecosystem of microbes. Chemolithotrophs, organisms that extract energy from inorganic chemical reactions rather than sunlight, have been found living in pores in rock at depths of 5 kilometers and more, eating iron sulfides and breathing sulfate, existing on timescales so slow that a single organism might divide once every 1,000 years. These organisms are not exotic hypotheticals. They are here living beneath our feet, discovered alive in drill cores and mine shafts. The deep subsurface biosphere, by some estimates, contains as much biomass as the entire surface biosphere, all the forests, all the grasses, all the soil microbes, all the organisms in the ocean. We have found and studied only a fraction of it. The rest remains essentially unexplored. And if Earth's deep subsurface hosts this kind of life, chemically driven, metabolically slow, adapted to extremes of pressure and temperature, then the case for similar life in the subsurface of Mars or the subsurface oceans of icy moons becomes much stronger. The question shifts from whether such life is possible to whether the conditions are right. On Mars, the subsurface is shielded from the surface radiation that makes the surface so hostile to life as we know it. The pressure increases with depth in a way that allows liquid water to exist at higher temperatures than on the surface. Geological heat from the planet's interior, which InSight has confirmed still exists, provides a potential energy source. Minerals in the deep rock could support chemolithotropic metabolism analogous to what drives the deep biosphere on Earth. If Mars ever harbored surface life and that life was driven underground as the surface became inhospitable, the deep Martian subsurface could still harbor it today, slowly metabolizing, slowly reproducing, invisible to any rover operating on the surface, waiting for an instrument capable of reaching it, drilling deep into Mars. The kind of deep that would be needed to sample this hypothetical deep biosphere is not possible with current technology in the Mars surface mission context. The InSight drill, which was designed to penetrate 5 meters into the Martian soil, became stuck at less than half a meter due to the unexpected physical properties of the Martian regolith. A drill capable of reaching the depths where liquid water might persist would need to be far more powerful, far more autonomous, and far more robust than anything yet built for planetary exploration. This is a technology development challenge. It is not an insuperable one. This is part of what makes the current era of Mars exploration feel like a prelude rather than a conclusion. Everything accomplished so far, the orbiters, the rovers, the landers, the helicopters, has been surface and near-surface reconnaissance. The deep interior of Mars, the deep subsurface of Mars, the chemistry of its ancient ocean sediments at depths accessible only through drilling. The isotopic record preserved in its polar ice cores. All of this remains largely unexamined. The planet has given us answers, and each answer has produced new questions of greater depth and specificity. This is perhaps the most honest way to characterize the current state of Mars science. Not a story of resolution, but a story of progressive refinement, each mission reducing the range of possibilities, sharpening the boundaries of what we know and do not know, pointing toward the questions that the next generation of missions must answer. The element most often proposed as an alternative to carbon is silicon. The comparison has a solid chemical basis. Silicon sits directly below carbon in the periodic table, meaning it has the same valence electron configuration and can form the same 4 simultaneous bonds. Silicon can form long-chain molecules, it can form ring structures. It forms compounds analogous to many important carbon-based molecules. Silanes correspond to alkanes, silicates correspond to carbonates, silicones, familiar to anyone who has handled kitchen equipment or medical devices, are silicon-oxygen polymer chains analogous to some carbon-oxygen polymers. The German astrophysicist Julius Schreiner proposed silicon-based life as early as 1891, noting the structural similarity between the two elements and the possibility that silicon chemistry might operate under conditions too extreme for carbon compounds to survive. Silicon bonds are generally stronger than carbon bonds, meaning silicon-based molecules would be more stable at high temperatures. Silicon compounds can remain chemically active at temperatures that would destroy organic molecules. These properties make silicon an interesting candidate for life on hot, high-pressure planets, the kind of environments that carbon chemistry cannot tolerate. The analogy breaks down in important places. The most critical involves the oxides. Carbon dioxide, the product of carbon reacting with oxygen, is a gas at most biologically relevant temperatures and pressures. It can be expelled from a cell, exhaled from a lung, dissolved in water and carried in blood. It is easy to remove from a biological system. Silicon dioxide, the product of silicon reacting with oxygen, is quartz. Ordinary sand, solid at almost any temperature life is likely to encounter. A silicon-based organism metabolizing oxygen would produce solid silicon dioxide as a waste product. There is no obvious way to expel this material from a cell, the way a carbon-based organism expels carbon dioxide. The respiratory architecture of a silicon-based life form, if one exists, would need to be fundamentally different from anything on Earth, and the specific mechanisms are not easy to envision. Silicon chemistry is also generally slower than carbon chemistry under comparable conditions. Chemical reaction rates decrease as temperatures fall, and silicon compounds are already less reactive than their carbon equivalents. In cold environments, this could mean metabolic processes unfolding on timescales far beyond what we would recognize as biological activity. A silicon-based organism's generation time might be measured not in hours or years, but in millennia. A chemical signal passed between two neighboring organisms might take weeks to transmit and interpret. An ecosystem of such organisms, if one existed, would be essentially invisible on human timescales. It would look from the outside like inert rock. But chemistry is not life, and slow chemistry is not impossible life. In environments without oxygen, reducing atmospheres dominated by hydrogen, methane, nitrogen, the oxidation problem disappears. Silicon compounds can remain stable and reactive for enormous periods under the right conditions. The universe contains countless environments that are nothing like Earth's surface. The possibility of silicon-based life has not been ruled out. It has only been found implausible under conditions we are familiar with. If the universal solvent is not water, what might substitute for it? The most thoroughly studied candidate is ammonia, a molecule consisting of one nitrogen atom bonded to 3 hydrogen atoms. On Earth, ammonia is a pungent gas at room temperature, but at minus 33 degrees Celsius and standard pressure, it is a liquid. At higher pressures, it remains liquid at higher temperatures. And in the outer solar system, ammonia is abundant present in the atmospheres of the gas giants, in the composition of comets, in the ice mixtures of moons orbiting Jupiter and Saturn. Liquid ammonia is a capable solvent. It dissolves many of the same classes of compounds as water. It forms hydrogen bonds which are critical in giving proteins and nucleic acids their three-dimensional shape. It supports an acid-base chemistry analogous to the acid-base chemistry that drives many of Earth's metabolic reactions. Biologist J.B.S. Haldane, one of the founders of population genetics, proposed in 1954 that ammonia could serve as the basis for biochemistry on cold planets, and the proposal has been developed further since. An organism based on ammonia chemistry would live at temperatures that would kill any Earth organism instantly. It would breed something other than oxygen, nitrogen perhaps, or hydrogen. It would drink ammonia instead of water. And liquid water encountered on a warm planet would be to such an organism what concentrated sulfuric acid is to us. A violently reactive substance that would attack its internal chemistry and destroy the molecular structures it depends on. Earth, with its surface covered in liquid water and its atmosphere saturated with water vapor, would be an almost instantly lethal environment for any ammonia-based life form that arrived here. Ethanol has been proposed as another potential biological solvent, particularly for environments in an intermediate temperature range. It is a good solvent for organic molecules, somewhat less reactive than water, and chemically stable across a useful range of conditions. The challenges are familiar. The biochemistry built around ethanol would need to be fundamentally different from terrestrial biochemistry, and the presence of water, abundant in many cosmic environments, would be toxic rather than benign. One of the more exotic proposals in astrobiology involves boron hydrides, compounds in which boron and hydrogen bond in ways that create structures analogous to simple organic molecules. Some boron hydrides form cage structures, sheet structures, and chain structures that could, in principle, support a complex chemistry at very low temperatures in non-oxidizing environments. Boron is uncommon in the universe, much rarer than carbon, silicon, oxygen, or nitrogen, which makes it an unlikely basis for widespread life. But in a reducing atmosphere at very low temperatures, boron hydride chemistry can be rich and complex. The catch is severe. In the presence of oxygen or water, boron hydrides oxidize violently. Contact with Earth's atmosphere would be catastrophic for any organism built on this foundation. All of these alternatives, silicon chemistry, ammonia solvents, ethanol solvents, boron hydride structures, share a common feature. They are adapted to environments that from Earth's perspective are extreme: high temperatures, low temperatures, corrosive atmospheres, reducing conditions, pressures far above or far below those at Earth's surface. On Earth, we call these environments extreme, and the organisms adapted to them extremophiles. From a cosmic perspective, these might be the normal environments. Earth's surface, with its temperate oceans, its oxygen-rich atmosphere, its moderate pressure, might be the unusual case. The implications for what we might find or fail to recognize if we found it are significant. A life form based on silicon chemistry, living in the high-pressure, high-temperature interior of a planet, would not look like a bacterium or a plant or an animal. It might look like a crystal. It might look like a slowly growing mineral deposit. It might show no obvious signs of metabolism on any time scale a human expedition could observe. We might walk past it, collect samples of it, and analyze it, and not know what we had found because we would be looking for the wrong things. This is part of what makes Perseverance's sample collection program so important. The samples being cached on the surface of Jezero crater are not going to be analyzed by a rover instrument. They are going to be returned to Earth by a future mission and analyzed in laboratories with techniques that have not yet been applied to Martian material mass spectrometry, isotope analysis, electron microscopy, organic chemistry assays capable of detecting molecular structures at concentrations far below anything a rover can measure. If Mars once harbored life, the evidence may be there in the rock, written in chemistry so subtle that only the most sensitive instruments on Earth can read it. At this moment, 2 rovers are operating on the Martian surface. Curiosity continues its exploration of the layered sedimentary record in Gale crater, drilling into rocks that formed at the bottom of a lake more than 3 billion years ago, searching for organic molecules preserved through geological time. Perseverance is working through the Jezero River Delta, collecting and caching its carefully chosen sample set. Above the planet, a fleet of orbiters from multiple nations continues its unbroken vigil, mapping, monitoring, measuring. The aggregate of what these missions have returned represents the most detailed portrait of another planet in human history. We know Mars in ways that would have seemed like science fiction 2 generations ago. We know its weather patterns and seasonal cycles. We know the chemistry of its ancient rocks and the age of its craters. We know where its water went and roughly when. We know the size and composition of its interior. We know the structure of its atmosphere at altitudes ranging from the surface to the edge of space. We know its radiation environment with a precision that allows mission planners to calculate the health risks to a human crew with reasonable accuracy. What we do not know is whether anything ever lived there. That question, the one that has motivated every mission, the one that has driven billions of dollars of investment and decades of engineering and the careers of thousands of scientists, has not yet been answered. But we are closer to answering it than we have ever been. The samples sitting in their titanium tubes on the floor of Jezero crater may contain that answer. The missions being planned to retrieve them may deliver it. And behind those missions, moving more slowly but with more certainty than any unmanned program could convey, human beings are making preparations to go there themselves. The distance between Earth and Mars at an average close approach is roughly 78 million kilometers. Light covers that distance in 4 minutes. A radio signal takes the same time. The journey by spacecraft takes months. But in the history of exploration, the journey has never been the limiting factor. What limits exploration is the will to undertake it and the capacity to survive what the journey finds. 100 years ago, no human being had ever left the surface of the Earth. 50 years ago, 12 human beings had walked on the Moon, and unmanned spacecraft were returning images from the surface of Mars for the first time. Today, we have machines drilling into Martian rock, making oxygen from Martian air, listening to the vibration of Martian earthquakes, flying helicopters in the Martian sky. The question of whether human footprints will someday appear in the dust of Jezero crater is no longer whether it is physically possible. It is a question of when and of what we are willing to pay in money and risk and time to make it happen. Mars is waiting. It has been waiting for 4 billion years. And for the first time in the history of this solar system, something from the third planet is on its way.